Hello. This is the second part of two meetings focusing on how to teach logical thinking through Prolog and logic programming, primarily to non-computing science students. We've already had four presentations, and today we're going to have another five, and roughly this is the proposed order. I believe you can see it on your screen. So, Kristen, you're first.
Uh-huh.
You've already seen the list of, let me just find you in this presentation, this single Google Doc, which includes all of the presentations. And here we go.
Yeah,
Thank you,
great.
Christian. Over to you.
Okay, great. Thank you. Let me say that I reworked my presentation a little bit because of the last session, which was super inspirational, and also the email discussions that were going on afterwards. Okay, I start right away because we don't have so much time. Let me present some spotlights of my teaching approach. My target group are students of art and design, both BA and MA level. They are interested in my seminars but have no experience in programming or logic. They are very skeptical towards formal thinking and they reject top-down strategies because they are afraid it kills their creativity. The topic of my beginners seminar is how to compose aesthetic, interesting objects in a logical way. My main goal is to shape the skill of the students to think about composing in a clear and precise way. Overall, I use simple code to get them in touch with complex topics. Okay, I jump right away to the questions. First question, how do I introduce Prolog? I introduce Prolog not as a language, but as a system, a logic AI consisting of two components. The inference engine that works top down and represents backward reasoning, and the language that is based on FOL and that can be used to communicate with this engine in two complementary ways, declarative or procedural. Second question, do I teach problem solving and reasoning? Yes, this is the core thing of my teaching. I use Prolog as an interface to get the students in touch with logical thinking, especially with the concept of backward reasoning. In fact, the behavior of the inference engine forces the students to think very precisely and in a top-down backward reasoning manner about the composition of an image. This is what helps them to develop a precise mental model of this process of composition, which is a key skill in art and design. Dealing with backward reasoning shapes their skill to think in a clear and structured way about how to solve design problems. Design problems such as how to create interesting aesthetic output. Third question, how do I deal with symbolic syntax and natural language reading? I think understanding the concept of implication is key to get a grip on logic and LP. So there are sessions where we focus only on the language construct conclusion if condition, and where we examine different readings of it. For example, causal reading or defining reading. One example is looks interesting, bracket, thing, bracket, if. And the last question, do I think teaching formal semantics is needed? I think in order to communicate effectively with the inference engine, it is important to understand its behavior. Therefore, the students have to give presentations on unification, backtracking, depth-first search, and resolution. So I teach kind of operational semantics. This fosters their digital literacy on a fundamental level. Here it is okay if their explanations are informal. Okay, that's it so far. Thank you very much.
Thank you,
Thank you.
Christian. So it's interesting that you are the first presenter to make a very strong case for teaching reasoning and backward prologue style reasoning in particular. Uh, so I'm wondering whether anyone would like to address that point in the discussion here.
I agree.
Sorry, Bob, I did not quite use
Well, I just
teaching.
pointed out the focus of Christian's presentation is so different from the other focuses. Namely, he's very much promoting the idea that we should teach reasoning. And now, do you actually contrast backward with forward reasoning? So, for example, in mathematics, it's very common to present proofs starting from axioms, and lo and behold, you uncover the proof of the theorem magically out of nowhere, which seems very creative. But in
Yeah.
many cases, if you actually work backwards from the theorem itself, you find that you can probably, or in many cases, I've found you can systematically generate the proof of the theorem without having to think creatively at all. So this point about bottom up versus top down, and it's something that you haven't mentioned. In particular, you're focusing entirely on forward or
So
top down reasoning.
I would say that what I have found is that teaching bottom up becomes, I mean, the explanation itself becomes a little bit cumbersome. I mean, you have to, it's certainly a valuable thing to teach. Top down seems to be more straightforward, at least, to me. Maybe my bias, but eventually, so for example, when I teach students, I do teach, uh, you know, uh, top down and bottom up, but bottom up comes much later because now you have to talk about given this program, what are all the possible queries that you could answer, and then how do you compute that set? And so somehow, but top down is slightly easier and more natural to teach is what I've found, at least to beginning students.
If you look at top-down reasoning as goal-directed reasoning, then in a way it's not really backward. The opposition between backward and forward along implication lines is a bit artificial because we all act in a goal-driven way, right? So in that sense, you move towards the future to achieve your goal closer and closer.
I want to comment that we are losing a tremendous wealth of knowledge that students already usually have, in particular those students of linguistics, language, etc., but even primary elementary school students who are taught how to analyze a sentence. They write the sentence and they start marking, this is a subject, this is a predicate. Within that, they start marking, this is the article, this is the noun, blah, blah, blah. And they reach all the way to, I have a sentence. But likewise, they can very easily go from there to say a sentence is a subject plus a predicate, etc., etc. So they already have many of the concepts we need to teach top-down versus bottom-up, and even to teach just how inferential thinking, logical thinking, only the concept of a variable, the concept of a constant, of a function, because these structures, they create these sparse trees that can be gone through either top-down or bottom-up are already a function. I mean, we already have all the elementary concepts that we need to teach for our discipline if we look at how to teach children to analyze the sentence.
So that's a very interesting idea, I think, Veronica, that maybe teach, so after teaching top down derivation of a query, maybe at that point for this specific query show how we could have gone backwards bottom up. See
Actually, the other way around works beautifully. I have tried it for people in university, for students of philosophy and letters who had no idea, and like in the case of Christian, no inclination to learn to be
for
very formal, but
sentences,
yet they are
so
perfect.
sorry for it. So parsing it may work nicely, but see bottom up in a Prolog program, then you have to come up with the set semantics, all the things that you could potentially compute in one step, in two steps, three steps.
What I'm
Right.
saying
So
is
you
if
have a
you
lot more
start,
than so in the case of parsing, you have a single sentence and you can go top down or bottom up. So that part is very nice. But here you have to, bring in a lot more when you teach bottom up semantics. And so you have to teach more complex machinery then. That's what I was saying.
what I mean to say is that if you start with teaching them from what they know, and they also deal with semantics, they also can have a grammar that builds semantics,
Sure.
etc. Once they know that, what a grammar rule is, you go from there, okay, now let's change it a little bit, and you have an inference rule.
Right,
That's
right. So that's a
I don't
valid
mean to
point
teach
to use
everything
grammars.
through grammars. I mean, it's a starting point we're missing the beauty and the applicability of by focusing in directly logic.
Fair enough. Yes. Yeah.
I just had perhaps a slightly different question for Christian. Earlier on when you started, you talked about, did you say your students were apprehensive about the top down because creativity is bottom up? Did you say something along
Yes,
those lines? I was sort of interested in
yes,
that remark. And could you just elaborate on that a little bit, please?
yes, yes.
Do they
This,
say, why do they say that top down kills creativity?
yes, yes, exactly. This is exactly the mindset they have. They really reject any top-down strategy because they are afraid that it kills creativity. And the great thing about, so they are thinking all the time bottom up. This is really what they do naturally.
Could you elaborate that in the context of art and the things that they do?
Yes. So if you give them a blank piece of paper, they start to draw something, and then once something is there, they draw the next thing, they get the next idea, and so they add and add and add the things until something is there. So this is the bottom-up approach. The top-down, the backward reasoning approach, I always come up with the Michelangelo example. When Michelangelo says. When I see the block of marble, I already see the complete statue, and this is kind of backward reasoning because he sees what is there, and from there he has to work backwards to get to the statue, but he sees it already. So he has the conclusion, and now he has to work backwards to bring the conditions to life to get to the result.
Thank you.
And
It's interesting in programming, see, the bottom up is you have a bunch of libraries, okay, and you have certain primitives that the grounding in that is important. You know, if you know your primitives and you know your building blocks, that is the bottom up way, right? The
Mhm,
top down is certainly from the problem, and I understand that. But
mhm,
also understanding what your primitives are, so you don't rediscover the wheel. You say, oh yeah, Prolog, oh, you should know that there are a whole bunch of primitives that are in place. And then, your top down work, is perhaps made easier, and at least what especially as the problems are more difficult, then there are big building blocks for you to tap. So just a
Well,
remark.
thank you. I'm afraid we're going to have to move on. Otherwise, we'll
Sure,
have to
sure,
have
But
a.
sure.
but I think
Michael's
that
wanted to say
Michael had a
something.
question. Michael had a question for
Michael,
a
there's an
long time.
interesting comment also in the chat. So from Mario. So sorry, go ahead, Michael. Then maybe we can look at the chat comment also.
Let's see. Okay, so all right, just briefly. I mean, I get this later if I get a chance to talk. But we do teach theorem proving, manual theorem proving in our course on logic, and of course, the main lesson we teach is problem decomposition, backward reasoning, and so forth, because that sometimes helps people to understand how to prove a result. But the comment I wanted to make is that sometimes it's really useful to take what you know and figure out. So you use that information that you know to derive some conclusions to kind of guide you on the way. So we also teach forward. And what I wanted to say is it's not all backward, it's not all forward. You need them both when you're doing something like theorem proving. And of course, if you just look at tree structure in a search, sometimes the branching factor favors forward, sometimes it favors backwards. You want both. You don't want to say everything should be backward and it's all we should concentrate on. That would be a mistake. Also, obviously, we don't go the other direction either.
Agree with that. Yes, yeah, I think it's a good point. Yes, agree. So there's a quickly. I mean, there's an interesting point on the chat. Does this depend on the art form though? Statues are created subtractively, drawings are done additively. I think that's an interesting point.
No, it also holds for drawings
Okay.
and photography and whatever. And let me say, what Michael said, The great thing about the standard system of Prolog is that the students have to work backwards. They have to work top down. Because the inference engine forces them to do, and this is the great learning effect. In case of art and design, they really have to do construct the thing backwards.
Okay.
Thank you. Very exciting discussion. And I think we're going to be returning to this topic in the future over and over again, I hope. May I suggest we then have Manuel present his perspective on these issues.
All
Manuel.
right, thank you, Bob. All right, so the first question is about whether we start, we present only declaratively. So I think that this is different for different levels, primary, secondary school, college, non-CS, college CS, etc. But at all levels, in my opinion, I think the first step should always be declarative. So the dream, of declarativeness and so on should be taught first. So at the lowest levels, because we probably don't advance too much, maybe everything is, we just teach the declarative view. This is how I see it. That doesn't mean that we don't teach also explanations afterwards, like the why and so on, and show the concatenation of the reasoning, but that you want to have a pure declarative view if you can. Now, at the higher levels, I think we start with the declarative view and then introduce progressively the procedural semantics. Now, this brings an important issue that I always try to underline, which is that the procedural semantics, you can only ignore it if you're executing on a system that is as complete as possible. So, a system that does not get stuck on infinite branches when there is a solution that can be obtained in finite time. Now, if there's no solution, that's one thing. Or if there's only infinite branches with no solutions. But if there is a solution, you shouldn't get stuck in other infinite branches and so on. And unless you have a system like that, you cannot teach properly the declarative view. So this takes us to the point that traditional Prolog is not ideal for this, because in traditional Prolog, and David also mentioned, several of us mentioned it, it requires considering the operational semantics. So in Prolog, in traditional Prolog, you need to know the operational semantics to ensure that there any or all solutions are obtained. Even that one solution is obtained, you need often to think about the operational semantics. Bob, can you push it a bit up? Thank you. So now, fortunately, we have better tools nowadays. So in particular, we have Prologs that have modern additions like fair control rules, breadth first, iterative deepening, tabling. Now, Prolog with these tools is completely different. It frees us from the burden of having to consider the procedural aspects, at least during the first steps. And it could be all steps in the case of younger students, because that allows us working in a much more satisfactory way with the declarative semantics. And that was the point of our paper last year in PEG. Now, having said this, these systems are very, I think they're very appropriate if you can have a Prolog with, tabling and fair control rule and so on. Now, for younger students, of course, you need a little bit more. You may need syntactic adaptations, blockly, simplified syntax, logical English built on top of that. Now, ASP is also a good alternative, I think, for the declarative part. If you don't look at the operational, then at least for some programs, for the programs where it works. But we prefer to use Prolog just for the fact that it gives you a smooth way or a smooth path to also go into the operational semantics and programming and so on. So this possibility of making the whole trip with one system is what is attractive for us. Do you propose to teach problem solving and reasoning? Yes, of course. What else are we teaching here? So other people have elaborated quite a bit on this. We're teaching problem solving and so on. Would you focus on the symbolic syntax exclusively or emphasize the natural language reading? The natural language reading is fundamental. Because that's how we understand the programs. That's the explanation of the program declaratively with the matching with what we want to say. Now, it's not just natural language, but it could also be graphical. It could, like the Blockly and so on. So we can find other ways to offer the syntax, especially, or to avoid the symbolic syntax if it's too much, especially for the younger students. Do you believe there's a need to teach formal semantics? Again, I think it depends on the level. It's not the same in primary or secondary school, college CS, college non-CS, and so on, as Michael was saying, our case is the same. Our students, for example, at college level in CS, they have a logic course. They've seen proofs. They've seen forward, backwards. They're familiar with all these things. So on the other hand, for example, so they know all this when we get to LP. So we can build on this and then teach that you can also do programming, real programming here, algorithms and so on. On the other hand, for example, some of our master students that come from very different backgrounds have not. Sometimes, we have a master's in AI, for example, where we get students that have not seen formal logic before. So then you need adaptation. I mean, then you need the, and typically we have no time to teach formal semantics, really. I don't know exactly what you meant here, Bob, but we do teach operational semantics. We do teach that, and we do teach a little bit of what is the meaning of programs in the sense of the model and the ground sets, the ground facts that can be inferred from the clauses and so on. Now, there's no mention here of programming. Is only declarative adequate? I think I addressed that before, but it depends on the level. At early levels, the declarative view is the focus. But having said that, I think we all agree that the major beauty of Prolog and LP is that we can use it for both. You can use it to teach the declarative view and to teach the procedural view and the programming views. And to me, this is what distinguishes Prolog and LP from just teaching logic or just teaching programming in another paradigm. So if we don't do that, if we don't teach, provided the students are at the appropriate level and so on, if we don't teach both declarative and procedural and algorithms and real programming, then we're not teaching logic programming. I think we're teaching knowledge representation or Prolog, or something else that is not logic programming. So that's my point. We cannot throw away, if we throw away programming, we throw away the baby with the bathwater. That's my view, no? So
Okay. Thank you very much for that.
yeah.
May I pick you up on this point you mentioned about having various control strategies at an early stage so that you avoid going into these terrible loops? Wouldn't that open the door for also having Prolog systems with a bottom-up control solver, so that you could have one system, one Prolog, one trajectory, based on Prolog, which would allow teaching problem solving both bottom up and top down, both with depth first search or breadth first search or iterative deepening. Does that make
If
any
you're
sense
asking
to
me,
you?
Bob, I mean,
Yes.
my answer to that is yes. I mean, it's nice to have also some kind of bottom up. I think if you have tabling, you're getting pretty much that. So let's see. Blind bottom up, I think, is not very useful because you start computing all kinds of things, and normally it's very rare that you have a database, for example, you want to know everything that can be derived from that database. Gopal also mentioned this. That doesn't make a lot of sense. You normally have some question in mind, something that you want to know. So that's why they invented magic sets and so on to guide even bottom-up execution is guided. So if you have top-down guided bottom-up execution, that's exactly what we have in modern Prolog systems also. We can do that. So I think the answer is yes, provided it's top-down guided bottom-up execution. Tabling does that to some extent, fixed point engines do that to some extent. So we have all the machinery to do that in Prolog systems. Maybe we should expose it more. That may be
And yet Datalog is increasingly popular, without magic sets. So we're losing the Datalog community if we focus entirely on a Prolog like approach.
But then Datalog is probably, they're more interested in solving problems where it really set at a time computation is actually useful. So, I mean, for the applications they use it for, makes perfect sense to use bottom up. But if you want to teach programming and all that stuff, then I think bringing in top down operational semantics makes it easier to explain, especially if you're appealing to their prior knowledge of programming.
So Gopal, if I may add to that, there's two separate things. One thing is, set like computing all answers, set-based execution, let's say, and a different thing is bottom-up or top-down. So bottom-up is set-based and for all predicates.
Right.
Right. That's the thing that I don't think even in databases, nobody wants that. If you think of set-based So all solutions at the time, but for a particular thing that you want to know, a query to the database, then it's really top-down, set-based top-down, or top-down with all the answers or something like that, which is what that does make some sense. Although that's only if your data structures are finite. No, as soon as your data structures are infinite, you have variables and so on. You have to be incremental. That's why unification was invented to be able to get over that hump.
Right. And then see, that's the thing. Then you have to teach, the grounding operation, and it becomes
Yeah,
start
exactly.
becoming
Which is infinite.
complicated.
Or something just to get started, you have to do an infinite operation. I mean that is
So that's where
challenging.
I tend to teach it later so that they can.
Manuel,
By the way, one thing I forgot to mention that was in the paper is that SCASP is a great thing because it combines the advantages. Because of course there's the issue of negation and so on, and that rears up its ugly head eventually. And SCASP is, I think has the advantages of top down and the possibility of dealing with negation. It's not simple, but at least it does something useful.
Okay,
Manuel,
may I
had a
suggest
question.
that this opens the door for David, but yes, Bharat, maybe quickly if you could.
Just a very, very quick question. Manuel, it has to do with your remark at the beginning, when you said, it's important to have a complete, inference engine, right? And you were mentioning different strategies, maybe depth first, iterative deepening, and so forth. My limited experience, what do you think about, the students who start out? They make a lot of mistakes. And, you need a simple model in which they could debug their programs. And I think that's where, as the inference engine, the underlying engine gets more sophisticated, the ability to debug becomes harder. I don't know what your experience has been. And Prolog, notwithstanding all its criticisms, has a very simple model that makes it somewhat easier to debug.
I totally
What are your
agree.
thoughts about that?
Right. So if you stay on the declarative side, you cannot really do operational debugging because it's really hard in one place. Actually, our debugger in Chow, we have these rules and so on, but debugging them is a pain. So I totally agree with you, Bharat. But the thing is, then you have to debug declaratively. So you have to do declarative debugging. You ask things, you see what works, what doesn't work, and you try to piecemeal figure out and with some help from some declarative debugging system or by yourself, you're just in your wits, find the problem. But it is true that it's somewhat debugging is much easier with the
I
standard
only mention this
rule.
because we are trying to introduce to students who are totally unfamiliar and they're going to make lots of mistakes, and then what is the underlying tool that we present them with? Debugging should be simple, otherwise they'll be very frustrated with the tool.
But in this instance, you can change. So you just by changing something at the beginning of the file, you say, okay, I want to execute depth first, breadth first, iterative deepening. So you can put iterative, let's say iterative deepening, so that it's efficient and it finds all the solutions. And then you at least get around the non-termination, which is really difficult to debug. You cannot really debug that too easily.
Sure.
And then, once it's terminating and so on, then you can turn it to depth first and try to figure out why it's getting the wrong solution. Not it's terminating, but it's getting the wrong thing.
So you might be able to do declarative reading for and either bottom up or top down for things like data log. But when you have a complex list processing problem, good luck going bottom up with it. It's just not reasonable at all.
Thank
Just
you.
like
Thank
You
you.
have a functor somewhere, it goes bananas. So a functor and some variables, some existential variable,
David,
you're lost.
David, this is your chance to
Okay,
shake your head in agreement or disagreement, one way or another.
Right. First, to respond to Paul, tell that to the Datalog community. Okay, so
Well, they don't have lists, right? Datalog.
tell it the Datalog. They're doing interesting things. You don't call that computation. You don't call that logic. I do. It is constrained, but they're doing interesting things. So saying bottom up is completely useless, I think, is not a correct statement. However, people differ. Everybody does. Okay, what I took this task to be was to, or I interpreted it as, what can we teach to sort of the youngest children we can reasonably teach something to? You know, so I don't know exactly what age that is, but what's the simplest thing from logic programming that we can teach to people who don't have any background in what is it we want to teach from logic programming? We started about teaching computational, logical thinking and computational thinking. Okay, so I want to go back to that, and I think that's the space I'm wanting to think about. Okay, so I agree with everybody that said before, is that we first want to teach logic, the declarativeness, before we teach computation. And my thinking, and I completely disagree with Gopal, that bottom up is so much harder than top down. I completely disagree with that. Bottom up is iteration. You just keep doing something over and over again, and that is easy. Top down, you got to keep track of what you did, what you didn't do, what you're going to do, what you did, what you're going to do when you can't go where you're going. I mean, there's a whole lot of complicated stuff you got to keep in your mind if you're going to do top down. So anyway, I think for children, we're not teaching top down. For children, we're probably not even teaching, paying too much attention to the computation. My theory is that if you teach the meaning correctly, okay, so I teach semantics through forward chaining. We do have to, it's a very good point. I think Christian's point of we have to teach implication is a very important point. So implication is something we need to teach. And that's hard to teach. Laura has shown that even teachers have a hard time with rules, right? So, but I think without rules, we haven't taught what we want to teach. So I think we need to teach rules, and rules are based on implication, as we all know. So I think we need to try to teach implication. And then implication, it seems to me very natural to teach modus ponens. If we know A is B and we know B, then we conclude A. That is a relatively simple forward chaining thing. You know a fact, you know an implication of that fact, then you know the implication, the implied fact. And then you can chain that. So I think that's not too hard a concept. And then you can organize, then bottom-up computation is just organized forward chaining. You're going to do it in an organized way. You're going to do it in groups of things. You're not just going to do it randomly. You're going to do it methodically. You choose simple examples where you don't get explosion. Yes, if you build a database of a gazillion things, then it's going to be huge. For children, you don't build such a database. You choose something very simple so that the explosion does not overwhelm. And you don't have to do the whole thing. Once you get the idea of organizing forward chaining and bottom up, then I think that's enough. You can just give an example. Notice that we have a forward chain. Therefore, if we know this, we can conclude that. Okay, so that for the question about English, and do we use a formal language or an English, the way I would approach it is I would say, yes, we're doing English, and we talk about statements, simple declarative statements, and then you create a predicate by pulling noun phrases out of simple sentences, like the father of X is Y. You'd say the father of David is Henry. Okay, and so that's a statement, and then you can say, okay, I want to use blanks. So I create a template, and so then what is that? That's describes all the ways I can fill the blanks that make sense, that are true, that make sense. Okay, so I think that's a way of connecting English to predicates in a way. And so then instead of writing the father of David is Henry, you pull the things, this template in front and call that the predicate, and then you put the blank fillers after. You call those the whatever, the arguments, the objects. I don't think that's too hard, and that does give a formal language, and it also separates the English from the formal, which I think is important for kids to know, that English isn't formal. What we're doing is we're using it to make something formal. And so we now know whether we're just saying something or whether we're trying to say something precise. Maybe, maybe not. Teach knowledge representation or database design more than problem solving. I think that, and there I would now, after our discussions online, I would now say I think I want to teach truth representation. I think I would say we want to represent true things and convey the idea of truth conditional semantics. That is, a sentence is true if it corresponds to a true statement in the world. And we can talk about which world on that, but we're talking about true statements. And I think that's important. As a matter of fact, I read an editorial in the Times this morning about how we're completely losing the concept of truth and reality. I think it's important to teach children that there is a truth. There is a correspondence between statements and reality. And that's an important correspondence to us to be aware of and to know when it holds and when it doesn't. So I think teaching truth is an important concept. Okay, and again, are we teaching reasoning? I think this forward chaining idea is the reasoning. I think for children we teach it informally, other than you can see this is all, everything we can reason about this way is everything we can know. And I think that's a useful thing in it is that. So anyway, it's a simple idea of computation. It's not subtle. We're not trying to control some computer or anything. We're just trying to know what is inferable and what's not, what is true, given what we know. Okay, and I think it does go on to one more slide. I tried to keep on one slide, but I think if I noticed it went to another one. Bob, can you move to the next line? I think there's one paragraph that I have.
Right.
There it is,
There
yeah. Okay, so I was thinking about what kinds of examples would I use. I think Gopal and his emphasis on examples is great. That's exactly what we need to think about. So I was thinking about examples, and I was thinking about family trees and reachability. And then I was thinking about, a family tree is a graph, and then we can think about labeled graphs and talk about paths through labeled graphs. And then we can talk about what the labels are, and we can maybe do path sequences, labels on paths in a graph. And my granddaughters like to use beads to put together necklaces and bracelets of different shapes, of different patterns of colored beads. You could very nicely say, can we define, all the paths that start with 3 blues and then have any number of reds and ends with 3 blues? How would we do that? Anyway, so I think children might be able to visualize those and to write simple rules that define patterns that they might find interesting. And of course, it then goes on to grammars. We could look at spatial graphs, reachability, game graphs, etc. Anyway, so I don't know how that would work, but I thought that might be interesting. Okay, I'm done. You can take your pot shots.
Wow, there's quite a lot to take. I may just say I completely agree with you about bottom up versus top down. Bottom up is much more natural, much simpler than top down. If it's done, the way I would do it, let's say.
By the way, I mean, I'm not criticizing. Most of the other speakers today have talked about programming, and they're talking about more advanced students. And I agree very much about, like what Manuel was saying. I agree with almost all of that, but I don't think that's what we teach at the beginning. We don't teach programming at the beginning. I agree completely that we need to, that in order to teach programming, we need to teach top down. I really think that's where programming comes in. So that part, but I don't think we can teach programming to, elementary schools at the very first level. We shouldn't teach programming at the very first level. We should teach truth and description and precision. That's another thing that I think Christian said at the beginning that I thought was very important, is that we want to teach students how to be clear and precise. That's a very, very important idea and ability that I think a lot of students don't get. And if we start trying to teach it early, that would help.
So one problem that, again, Bharat pointed out that, students write something, they make mistakes. And so, I call it debugging by staring, that looking at the logic and convincing yourself it works correctly. And debugging by staring, works up to a certain point. Staring at the program works up to a certain point.
That's why we have bottom up. I mean, that's why there is a computation. That's why we do give the idea of bottom up computation, because that will tell you whether you defined it right or not. And we keep in problems small enough that the explosion doesn't kill us. That's
fair enough. Fair enough. Yeah.
That's the way I would try to do it.
So you're saying use bottom up for debugging the code?
Yes, use bottom up for debugging.
Okay, fair
and
enough.
it's important. I mean, and I think that really is a neat thing about our framework, is that we can connect definition to this computation, this inference. But we want a very simple computation. We don't want to get it so complicated they get lost in the details. We want it to be so they can just see, yeah, this implies this implies this. We have these two things, that implies that. We got that. And if you try to, if you show them you don't get that, then they say, why don't you? Well, and they have to think about what facts they don't have or what rules they don't have that they thought they had in order to get it.
It's possible that we have minds that think bottom up and minds that think top down. So there might be a dichotomy there.
Yeah, no,
it's an interesting experiment to conduct to find out how people think.
Yes. I think that, I guess one other thing I would say, and maybe this is my own particular hang up. As I said, I think bottom up is iteration and so bottom up is induction. You generate more and more things. Top down is induction upside down, which is called recursion, right? And I think when you teach mathematical induction to 7th graders or 8th graders or whatever grade you teach it now these days, you don't teach a top-down computation of induction. You teach, I know what factorial is right, because if you start with 0 and you add the rules again and again, you get up to the factorial that you wanted, and you get the formula, right? I mean, you get the number. So, but you don't say, I'm going to teach you factorial by backward chaining, top-down computation.
I would debate that. I might teach it as, say, that you want to compute factorial of n, assume that.
But in mathematics, you don't say compute. I mean, I don't remember when I first got induction in 8th grade or 9th grade, what they weren't talking about computing, they were talking about defining, right? We want to define factorial. And then how do you know you defined the right thing? And the way you define the right thing, at least the way I thought about it, was we start at the bottom and show that we're defining the right thing going up. It wasn't that we start at the top and say, oh, well, I would define the right thing if this was the right thing I defined. Oh, and that would be right if this were the right thing. And that would be right if this were the right thing. So I've now got this very long chain of ifs that I don't know whether it's right or not yet until I get to the bottom. That's hard. I know 0, I know 1, I know 2, I know 3. I don't get anything that might be wrong. They're all right as I'm going bottom up.
But David, so you have a predicate. Let's say you have a chain of predicates, and you want to know something about the top of the chain.
Yes.
Where do you start with the bottom up?
I'm not.
This is the problem. So that's why I mean top-down driven, bottom up. So you really need to go from what you want to prove and then you can reason bottom up for the recursions.
Also,
Yep. I guess again, I'm not I'm not trying to teach children to debug top Prolog programs. That's not what I'm trying to do. So I'm trying to teach children precise thinking, thinking about what truth means, and thinking about inferring truth.
No, I
That's
follow
what I'm
you,
trying to get
David,
them
and
to
I
think about.
totally agree. I totally agree. If you have a simple, predicate, and some facts and so on, that's the way to go.
Okay, and
And
I
we do
agree
it
with
like
you.
that, and we do
If you have a
inductively, and
programming
even
problem, you need to do top down. I agree with that completely.
yeah. But as soon as you have something that calls that, and something else that calls that, which will happen also in simple examples, you do have to do a little bit of, I think.
I think the examples we use won't be that deep, right?
Okay.
That's my contention.
No,
I may be wrong, but I think they won't be so deep that you
that's a
can't
good point. That's a good
follow
point.
you can't follow the thing. But I may be, and certainly when you get to programming, they are so deep you can't think about them bottom up.
I start with my students with the family example, no? And as
Yeah, that's the most.
immediately things get very complicated because they start thinking about uncles and you and relating sides of the tree and so on. It's like there's never a simple example.
I just have a remark along these lines.
We have to continue this discussion on
Michael
many
has
other occasions, I think, because otherwise Michael and Veronica are waiting in the queue, and I think Veronica, you're going to have a whole session to yourself if you don't mind. I think you'll have.
Not I'll write it up, but after the conference.
That might allow you to do justice to what you want to say. At this point, I suggest we give Michael the floor, or the internet, shall we say?
Okay, thanks, Bob. Yeah, I'm having just listened to that. However, I'm tempted to make my responses one word long after having heard David, and the one word is ditto. I agree so wholeheartedly with everything he said. My understanding of what Bob was asking was not how to teach programming and not how to teach logic programming, but rather how to teach critical thinking, how to teach logical thinking using elements of Prolog. And so what I decided to do was to make my remarks more along the lines of what are we doing in terms of teaching logical thinking and critical thinking. And so let me address that topic. First of all, a little bit of background. I don't know. I know that you're aware of some of the things we're doing here, but I just wanted to summarize them for you. Everything we do here is based around a course called Intro Logic, which we developed a few years ago. And that course it's for logic, not logic programming, logic. And we teach that course at Stanford to fulfill the logic requirement for undergrads, grads, and the general education requirement for all undergraduates. They also use a version of Intro Logic in a variety of high school summer camps for high school students. Usually those are 2 or 3 week intensive camps, some online, some in person. And the course is also available on the web from the Stanford site, as well as via Coursera, and originally OpenEdX, but it isn't there at the moment. It's been somewhat successful and it's reached a relatively large community. I should mention we also have a course on logic programming, but I don't want to confuse the two. Our course on logic programming is specifically designed to teach people how to program computers using logic programming. That's the goal. It's not to teach critical thinking. So it's not that what we're doing there is not really directly relevant to the conversation that I wanted to have, which is how do we teach critical thinking. The one other activity I wanted to mention was that we're also provide academic direction for a variety of different international competitions on logic that began a few years ago. You can scroll down a little bit, Bob. So the first of those that is run now. It's in its third year, going into its third year. Is the Senior Logic Olympiad, which is an annual international competition for high school students. We've had that 2 times now. It's growing reasonably well. This year we expect to see a much bigger growth because of the outreach that we've had. So far we've had some 4,500 participants, but that's like an order of magnitude fewer than what we expect it to be in the year or two to come. Next year there will be a Junior Logic Olympiad, which is for middle school students. So similar idea, nationwide. I'm sorry, international. But for middle school students, there's no plans to do an elementary school Olympiad, but we do have interest from regional partners in offering local contests, and so we're providing support for those. Okay, so those are the activities that are underway right now. Based on the reason I mention all those is you can scroll down, Bob, because I don't know, we teach everything with Hebron semantics. So we should talk about that at some point, explain why I think that's so important, why the logicists or the logicians are so uncomfortable, but also why we continue to do that because we think it has significant theoretical and pedagogical advantages. Okay, so having said that, what I want to spend my time really talking about is these logic competitions. And what we've had to do in order to make those competitions go forward is to produce a sort of a graduated syllabus of what should each student at each level know. And then what do we have to teach in order for them to know those things? So I wanted to tell you what we're working with right now and get your feedback, not necessarily today, but at any time you have on this syllabus would be great. But this is the one that's organizing the design of these 3 levels of competition. Okay, so first of all, let me start at the elementary school level. So the main goal here is, as I wrote here, is logic-related education. The main goal of that is to represent data about objects and relations and to solve problems about this. So we want to get them to think about the world in terms of objects and relations. So not necessarily numbers, not necessarily obsessed with functions as they would get in the rest of their education, but relationships between objects, not necessarily numbers, any old people liking other people and that sort of thing. And then the representations that we imagine is that they have formal representations, but they're not necessarily sentential. It could be graphs with pictograms for the nodes of the graphs, arcs representing different colors, kinds of arcs representing relationships and so forth. That's the level of formal representation. Could always use tables or simple sentences, but that's it. So we expect them to explicitly represent data. The definitions, constraints, goals, whatever are assumed to be described in natural language, not in a formal fashion. We're not trying to get them to write down definitions of things in a formal language. That's done entirely informally. The idea is to get them to take the representation of the data and to use that to solve problems of a variety of different sorts. That's the elementary school level. And those are the only kinds of problems. And that's based on a whole slew of different efforts that we've been looking at. The people write this at the Math Olympiad book for elementary school students and middle school students. When we go to the middle school, everything's pretty much the same, more sophisticated, more of that, but we now switch to the explicit representation of definitions and constraints and goals. So now we do expect them to write those things down that were in natural language and now in a formal language. And although it's not clear what that formal language should be, our inclination is to make it something like Datalog, safe, stratified Datalog, including negation as failure, importantly, because that's the right way to define fully defined concepts in terms of other concepts, grandparent in terms of parent, that sort of thing. So we are looking for them to formalize that stuff and then to begin to treat those definitions and constraints and goals as data, no longer just treating them informally, but they become the data. So here the idea is then, once they've got that, the idea is then to concentrate on solving problems with these representations. And here in the middle school level, we assume there's 2 kinds of problems that are solved, namely evaluation problems. You've got some data and definitions. How do you compute the results? Whether you're doing a top-down or bottom-up, one way or the other, compute those results. The other one is satisfaction problems, namely you got some constraints or goals and you want to find some data that actually achieves those, some plans or goals that achieve them. So the concentration is on evaluation upward or satisfaction downward. There's no discussion of theorem proving. There's no anticipation that people have any familiarity with techniques for doing general theorem proving. Then we go to the high school level, which is the senior Olympiad. And the high school level Everything is pretty much the same as before, but now we begin to concentrate on incomplete information. And this is the key element which I've been harping on in these meetings for some time, which is when we go to incomplete information, we need to represent that somehow, and that can include things like existentials and disjunctions, not as queries, but as in the data itself. So we're saying either John or Bill is the parent of Harry, and we don't know which. So we have to represent those disjunctions. We have to represent existentials. Because the information is incomplete, we need to eliminate negation as failure because we can't assume that things are complete. And so we go to a world without negation as failure using first order syntax, but Hebron semantics. And so at this level, that what needs to be taught is not necessarily Prolog and so forth, but rather what we're concerned with is theorem proving. So direct proofs, natural deduction proofs, the Fitch system plays a key role in education and in theorem proving at this level. This is manual theorem proving, notice. And yes, we do teach some resolution as well, but that is not the primary method. It's Fitch is the method. And here's where the comment I made earlier is that the techniques that are used for doing this are both bottom-up and top-down, exploratory, as well as goal-directed. Okay, and mathematical induction is taught here as well. Okay, so that's the main comments I wanted to make, was to suggest to you guys was this trichotomy of levels. First of all, at the elementary school level, representing data, but not necessarily definitions, but not explicitly representing rules and definitions and constraints. At the middle school level, we do begin to do that, but it's still complete information is assumed. When you go to the high school level, we now have incomplete information and all the techniques that are necessary in order to deal with incomplete information. And the questions on these Olympiads are based on these distinctions. Okay, I've used up a lot of time, so maybe I won't necessarily go through the answers to Bob's questions. Yes, yes, symbolic, and yes.
Okay. This idea of dropping negation as failure seems a pity, because you could give it the epistemic interpretation instead of understanding not P as not P. You understand it as not known that P, in which case it's totally compatible with classical logic. There's no need to introduce negation as failure and then lose it, because it had the epistemic interpretation continues to hold even with incomplete information.
Yes, but we have to get the focus on how to handle it. All the intellectual effort at that level is trying to deal with the rules for dealing with disjunction and dealing with existentials. This is by far the most complicated part of the reasoning, and trying to bring in the distinction between classical negation and negation as failure, having to do it, as you say, epistemically, is just a complexity that is too much. At least when we're teaching this in these summer schools, these 2 or 3 week camps, it's just too much. And so we definitely can't do that. Yes, when we get to the undergraduate level, particularly advanced undergraduate level, yes, we can do that and begin to talk about ASP and so forth. But at this level, it's just too complicated to try to mix the two together.
So what I would get related to both David's and Michael's thing is that the logical reading, something as simple as just staring at the formulas. I don't know if it's attributed to Alan Coleman, but when you have an error, you don't debug, you just think more. And that actually works in quite a few situations. So the fact that you focus on the logical reading rather than the semantics or the detail, means you understand the implications at least, is in an interesting way not a problem if it's bottom up or top down, really. You just look at that logical statement from left to right or right to left and what it actually means to you. So anyway.
Yeah, so I should say you mentioned the idea of debugging and so forth, and yes, there is an element of that here, that you wrote the wrong things down. If you can't prove the result, maybe that's because you didn't write enough down, or you wrote down an inconsistency. And so there is an element of debugging. But frankly, at the level that we're talking about, high school students and so forth, it's not debugging, not that they're writing the wrong thing, but their concentration primarily is how do you prove what you want to prove? How do you determine what you want to prove? And by the way, it's not all theorem proving. There's a lot of concentration on truth tables and logic grids and other techniques for doing logical reasoning rather than just writing formal proofs. So we're concentrating on all those different techniques, but the problem is they want to solve a problem. They're not debugging so much their representation, although there is a lot of concentration on writing the right representation. But the result is you can't prove what you want to prove, so you wrote the wrong thing down. But a lot of it is we give you this stuff, you figure out how to prove it. Or determine the answer, whichever technique you're using. Well, anyway, my request to you all is if you folks have any suggestions on this gradation of topics, this graduated syllabus, and what is expected of students at each level, you should let us know because they are, in fact, informing the questions that we're asking of these kids on these various different levels of competition. Again, we're guided a lot by the many publications that have already been produced for educators at this level, but coming at it with a different perspective from the computer science and logic programming world.
Well, I would like to just reiterate that I think that the discontinuity between the middle school and the high school is not necessary, and that, for example, existential datalog shows one direction in which one can introduce existential information, and similarly, ASP's use of disjunctive conclusions. I mean, there should be a more gentle transition from one to the other, rather than a totally unrelated.
Bob, you and I have been talking about this for years, and I'm very sympathetic to that point of view. I've been struggling with this for a topic for a very long time, but ASP is not the solution to this. ASP is a good solution to a problem, but not at the high school level. It's too confusing. And you got to get.
I'm not suggesting ASP, but I'm suggesting that ASP does allow one. Yes, one can take things out of ASP and put them into Prolog, if you like.
That might be yeah. So let me point out that a lot of what we're doing, Fitch reasoning, is what we concentrate on, not SL resolution, because it's a lot simpler for people who are trying to prove theorems, practical theorems themselves, as opposed to making their computers do it. So I think there is an issue there, but I wanted to flip this whole thing over. Actually, what we teach is FOL with Hermenegildo semantics without negation as failure. And what we're trying to do now is bring Datalog and Prolog into it at an earlier stage. So it's not like we're losing negation as failure. We're actually adding it in when we go from the high school level down to the middle school level. Because at the middle school level, you don't have to worry about incomplete information. You can have negation as failure, and everything's a lot simpler. So it's actually a good result. It's not like we're losing it. We're actually gaining it on the way down. Maybe I should have given my presentation backwards.
Michael, can I ask you a simple question about critical thinking and logic? How far can you go with this propositional logic in the introduction of logical thinking? Because I can write a lot of things and reason interesting problem situations purely in propositional logic. Can you just comment at what point you just gotta have to break away from that, from proposition?
Yeah, so I agree with you. In the very short, people request sometimes a very short introduction to logic, and we just do propositional logic because you can teach so many ideas in propositional logic.
And so much about reasoning and thinking. Absolutely. And writing things down.
The difference between logical entailment and consistency checking and all those things, we can introduce all those ideas with propositional logic. We don't ever have to do anything more. So I think we can go a very long ways. I will say one thing, which is the way we teach it normally is at 3 levels. We teach propositional logic. We then teach relational logic, no functions at all, just basically Datalog level. Just Datalog. But finite worlds. Finite vocabulary, so you have a finite world, which is equivalent to propositional logic. So now you get the notation of mathematical notation, Prolog, Datalog, and so forth, without the functions. But it's still, propositional is still fully decidable. And only then people say, well, how am I going to deal with the integers? And we say, okay, well, guess what? We have to put functions in there. And now we introduce integers and we can create integers and go from there. Then propositional logic is gone. But up to that point, everything is done. And I think that's the way we should be doing this, and not being obsessed with, as many of the logicians are, with going straight to full first order logic.
Yeah. Yeah, thank you, Fedor.
I could talk on about this.
Well, we have run over the hour,
Right.
and Veronica has got another hour to herself. I think is a good way of looking at it.
It probably won't take as much unless you argue and argue forever, which is possible.
So let's leave it at that, and thank everybody. Oh, don't forget, Gopal, can you send us the chat, because there's a danger that
Yes.
we'll lose all of that if we're not careful. You're
It
muted,
would,
Gopal.
yeah, it would be nice to actually include somehow the chat in the video also. I don't know how that
Yeah.
can be done, but the
Well,
chat
we
is
can have
interesting.
it. Maybe in the next session we can go through the chat, as well as give Veronica her
Okay,
chance to. So that's another way of.
I'm gonna
of
email
in-
the chat because for some reason the chat disappears.
Yeah.
Okay, I have copied it. Okay, wonderful. And